final has been prepared already, and all the answers you can find in the lectures and homework. So it's a good news, right? So everyone already have the answers. And today we will have a review, and most of the content we have been discussed and reviewed already. And let's see how well we understand all the material. And for the final, it will cover 4 sections from the virtual memory, complex capitalizing, the ILP techniques, and the VLP techniques. And we have already discussed, especially in the first 3. We have one review session, right? And we have quiz 2, which already covers those 3 sections. And firstly, let's look at the virtual memory, see how well we understand. And this is actually this slide we have already showed it many times. I'm not sure if we show it in this way, still everyone understand. So, for example, for the virtual memory space, it is divided into which kind of unit, and for the physical address space, what it is. And also, if we would like to access a unit in a virtual memory on the virtual page, which is not in the memory but on the disk, then what we call it? So first, so what's this? The page, right? And for the virtual memory, it's the frame. And for the page fault access, we call it a demanding page. Right. And we have discussed the definition of page fault as well as the page hit. The page hit is the opposite of page fault. So in our quiz 2, we have this question. So choose the correct relations. Instead of, in our class, we talk about the relation between the page size and the virtual memory size, which is page hit. And in our quiz, we talk about the page fault. So in general, the page fault is 1 minus page hit. So the relation is kind of opposite, the trend. And for the memory part 2 is the address translation. This is the model of address translation. The P is defined the size of page, and N is the virtual address limit, and M is the physical address limit. Once we know the size of the page size, once we know the page size, for example, 64K per each page, then we can calculate what's the number of what's the value of P, right? And also given the definition of virtual page number and the physical page number, we can calculate all those physical page number and the virtual page number. In our class, we have all those examples. Everyone should be expecting to be able to calculate those values. And the page translation hits. In the hit case, we will have 5 stages to get the value of the unit of the value of the unit in the memory. And in the page fault, it has 7 stages, right? And one difference is if there is a page fault happen, we won't get the value. This is one significant difference between the page fault and the page hit. The Clarke algorithm. The Clarke algorithm we have exercised in the homework, and also we tested in our quiz 2. So So for the clock algorithm, let's look at the exercise in our home 3. Here is our homework, and here is the solution of the homework, right? And the first value is the value we would like to access, and the remaining table is the page table. And the initial status here, we will say it's empty. And when we would like to access A, we know it's empty, and a page fault happened. And we put the values of A here, and set the page as 1. And the same for B, C, and D. For the first page fault, we call it a cold start page fault. It's very close to the cache miss, right? When we power off the cache, and the cache is empty, and all what kind of access will be missed, and we call it cold start cache miss. The same here. This is cold start page fault. The first four are the cold start page fault, and for the fifth and the sixth, those are the page hit. And for the last 6, those are 6 page faults. So in total, we have 10 page faults here. And especially first 4 called the start page fault. And one thing we would like to emphasize is the clock algorithm is a replacement algorithm. Means we will not use it unless we need to replace an element. For example, here in the first 4 clock cycles, the page is not full, so we won't use clock algorithm. The clock algorithm start to use after the 4th clock. The complex pipeline. The complex pipeline, we already discussed this architecture, and it has the multiple paths, and for the execution stage, it's not necessary to finish in 1 clock cycle. And we have one example to analyze the data header in a code. And those are all the relations, including the read after write, the write after read, and the write after write patterns. And based on the relation we figured out here we can have instructor dependency graph. And this independent graph describes all the relations among instructions. And one question raised by the student is whether the instruction 3 and the instruction 4, they are dependent or independent. Obviously, here we can see they share the same operand here, right? And they are somehow dependent with each other. But they are not, this dependency does not belong to any kind of those 3. So if we say whether they depend on each other, they have dependency, yes, but they don't have either of those 3 data headers here. So that's why here once we talk about optimal order, optimal order execution here, we didn't consider the swap between 3 and 4. And here is the optimal order completion. Auto completion means they will be issued in sequence. You can see always 2 will be issued after 1, right? But 2 can be finished earlier than the instruction. out-of-order completion. So we can see with the out-of-order completion strategies, the performance can be changed. And also we need to do this exercise on our own to understand how the out-of-order exclusion or completion works in the code. The scoreboard, we have many exercises with this scoreboard dynamics already. This is the way to manage the hazard and the exclusion sequence in the code. And we have this we have the question in the tutorial. So those are all about the complex pipelining. Let's look at the IRP. The first part is out-of-order exclusion. It's kind of related to previous what we discussed. And here is one example, and we don't need to re-overemphasize this, right? And this is one access. One thing we changed is here we only have one add and one multiplier. Besides the data hazard, we also need to consider the structure hazard when this code is good.
I mean, is it possible to like go over the out of order, in order execution?
In this lecture, no, because we already discussed it many times, and we have many exercises to work on. If you still have questions, we can discuss it offline. And the renaming. Here is a quick example to show how can we address the lack of register number issues and to resolve the data hazards. For example, here, once the F4 becomes F4 prime with a different number, then the relation, the dependency between 3 and 5 will get released, and we can gain the performance improvement from this renaming. And for the renaming, we would like to introduce the reorder buffer, and here is the structure of the reorder buffer. And here is how can we use the renaming table along with the reorder buffer to resolve the identify the data hazard, the true data hazard in the code. And here those are the exclusion procedure. We won't go to it in detail. And the last part is about the 3-stage in the complex pipeline in the multi-cycle out-of-order exclusion. So in general, we have here we redefine stage as issue stage, exclusion stage, and commitment stage. We designed it in this way because for the issue stage and the commitment stage, it has to be done in order. And for the exclusion part, it can be done out of order with the scoreboard. And the second topic in the IRP is the process interrupt and exception. And here is the definition of the process interrupt. It means if there is an interrupt at I, and all instructions before I, including I, have to be finished, and any instruction after I cannot be done. And in order to reach the process exception and interrupt, we come up with this architecture. So at each stage, it's possible to generate the exceptions or interrupt, but all of them will be passed to this stage after the M. And all the interrupt and exception will be processed here before the commitment or the red flag. And the EPC here represents the exception program counter. And also we will record which kind of cause to get this exception. And all the previous exception flag will override all the later exception flags. And here is the in-order commitment for the process exception. The similar ideas as the previous one. And here we can see all the exceptions will be processed here, and all the preloaded instruction will be queued if there is an exception identified. And here is about the mixed branches and jumps. And regard the jump, the JR, and the branch conditions, we need to know when we know the direction of the branch, and also when we will get to know the target. So here is another exercise here. So let's say when will we know the target address, and in this case, for example, if we know the target address after the branch address calculation D, so we will say after B, or at the B stage we will know what's the address. And when will we know the direction? If it's we need to get the values of register files at the R stage, we define it after R we will know. So make sure at which stage we will get the target address and the branch direction. The last one is about the branch prediction. The branch prediction, the first is the static branch prediction, which is encoded in the ISA. And in our class, we focus on the dynamic branch prediction, taking advantage of temporal correlation and the spatial correlation. And here is the first hardware we introduced, the branch prediction bit. And in this example, we have two branch prediction bits. And here is one way to implement the conversion of the branch prediction state here. From the taken right to the untaken right. We can see the transition between them. And based on the prediction bit, this is the first complete hardware solution we come up with. Called the branch history table. And for the branch history table, we will use the k-bits to examine all those 2D entries to see which one will be indexed for this PC. So which entry will be selected depends on the PC value only. And as for the target, what's the target address? This result will depend on the contents of the instruction. Means we have to fetch the instruction, guess this instruction, extract the offset, and then add the offset with the current PC value to get the target PC. So we can look at a very concrete example. So here is our branch history table, right? We just discussed. And let's assume right now the k equal to 3. Means here we will have in total 2, 2, 3, 8 entries, right? And for the current PC, because it's 32 bits, so the last two will be always 0, and then we will look at another another 3 bits here. Let's say if the bits here is 1, 0, 1, 0, and it means the entries here is 0, 0, 0, 0, 0, 0, 1, and 0, 1, 0. So this address, this PC values will index to the third entry in the branch history table. And depends on the value here. For example, if the value here is 1, 0, then this PC will be, this instruction will be predicted as taken, because the first one is 1, right? And so based on the the last 5 digits, we get to know this PC is predicted as taken. And as for the target address, we will use the PC value to fetch the instruction and get the offset and calculate the result. So here is the way how the fetch history table works. And for the first part, it can be done after we know the PC value. For the second part, it will be done after we fetch the instruction. So any questions about this table? Here is another design, the 2-level branch prediction. It has a very close idea as the previous one. The same thing here. We will use the, for example, if k is to 3, then we will use this 3 digits to index which entry will be used for the prediction. And also to global register, the branch history register, to determine which column it will be selected. For example, here, each column is labeled as 0, 0, 0, 1, 1, 0, and 1, 1. And for the previous 2 prediction, if 1 is taken and 1 is not taken, and then we will select the third column as the prediction table. So this entry will be read to predict the direction of this instruction. So once we come up with a very concrete example, I very much will be able to understand how this branch predictor works. Here is a limitation of the branch history table, and we know we will know whether it's we will know whether it's be correctly predicted or not after B, and we will have the jump register penalties after R. So the penalty for the taken or not taken is 4 clock cycles. And for the JR, the penalty is 7. Because for the predictor, we have to done it after the instruction fetch, right? So here is another more efficient and effective design for the branch prediction called the branch target buffer. The branch target buffer, firstly, it will only use the PC value to do the prediction. No, we don't need to do any fetch, instruction fetch. This is the first difference. The second difference is in each index, it will have the prediction bit as well as predicted target here. So once we get the PC value, we will use the k bit to see which entry we will use. We will know whether it's taken or not taken, the direction of the branch, as well as the target if it's taken. And here is another enhanced design. Besides, we only look at the last k. We will also compare the PC with the pre-saved PC value, see if they are matched. This is the way to let this table only deal with the